Gravity. A mysterious force among the four fundamental forces, namely weak nuclear force, strong nuclear force, electromagnetic force, and gravity. This force can attract everything to itself regardless of their material or weight, without having any physical contact with objects. Just like when something is released from your hand, you observe it being pulled towards the ground. But why? What is the true nature of this mysterious force? Is there an unseen hand that pulls everything towards itself, or is there a physical reason for it to exist? If you're interested in understanding how this force enters objects and how it was discovered, be sure to stay with us until the end of the video. Subscribe to the channel and like the video to support us. And don't forget to share it with your friends too. Isaac Newton, one of the most unparalleled physicists who has ever lived on Earth. Isaac Newton, who lived in the 17th century AD, from the beginning, all scientists and professors, including those from the University of Cambridge, England, were amazed by his intelligence and talent. This great scientist, who spent most of his time working on mathematical and physical equations, was once walking in the garden of his house when he noticed an apple falling from a tree to the ground, and suddenly he got lost in thought. In his mind, he pondered the question of why the apple, when it fell from the tree, didn't go upwards, or why it didn't fall a meter or two to the side, but instead followed a straight path down to the ground. And this was the key that formed in his mind, leading him to write his equations on gravity at the age of 23, in the year 1666 AD, and discover gravity. Until today, humanity owes much of its progress in fields such as aviation, rocket propulsion, construction of skyscrapers, and so forth to this great scientist. But now, let's examine together what gravity is, according to him, and how he defines it. Newton discovered that any object with mass can exert a force called gravitational force on the objects around it. The equations he derived for it were in this form. The force exerted by object A on object B is equal to the product of their masses multiplied by a constant called g, divided by the square of the distance between them. As these two objects move further apart from each other, this force will decrease more and more. For example, if the distance between A and B doubles, the force between them will decrease by a factor of 4, and if we triple their distance, the force between them will decrease by a factor of 9. This was one of Newton's primary equations regarding gravity. But when we try to apply these equations in very large dimensions, we find that they no longer work properly. Does this mean that Newton's equations were wrong? To answer this question, let me provide you with a simple example. All of you use GPS at least once a day to find your precise location. But it's interesting to know that this system is by no means compatible with Mr. Newton's equations. And if you were to use his equations, you would never be able to determine your precise location. So we've learned that Newton's equations work accurately and without any errors in small-scale dimensions. However, they don't work properly in large dimensions and long distances from a gravitational reference point. So how can we pinpoint our location so accurately now? By using Einstein's general theory of relativity, one of the brilliant scientists who has made great achievements in the field of physics, especially in light and gravity, and I have always been amazed by this great scientist. Now let's see together what these equations of general relativity are and how they work. To answer this question, first you need to become familiar with the concept of space-time. We all know that the space around us is extended in 3 dimensions, called height, length, and width. However, Einstein discovered in 1905, 400 years after Newton's discovery, that the space around us is 4-dimensional, and time is the 4th dimension. But because we are three-dimensional beings, we have no mastery over the fourth dimension, and we can only perceive it. Einstein said that the entire universe, even the empty spaces within it, is formed by a structure called space-time, which is woven together like the fabric of a cloth. Imagine this fabric of space-time spread out in two dimensions. When no mass is placed on this space-time fabric, it will not bend. But as soon as a mass is placed on it, the fabric will bend, and it will attract any object around it towards itself. Space-time in three dimensions, which is the universe we live in, is a bit more complex and takes on this form. For example, the Sun, which is a very massive object, bends space-time and attracts all the planets and celestial bodies in the solar system towards itself. The same example applies to the Moon and the Earth. Because the Earth is much more massive than the Moon has fallen into the Earth's gravitational well, causing it to orbit around the Earth. Now that we have understood the nature of space-time and gravitational fields, let's examine together what relevance these topics have to GPS satellites. As we mentioned, a massive object can bend the space-time around it. When space-time is curved, time also becomes curved. The closer we are to this curvature, time will pass slower for us compared to someone who is farther away from this curvature. This means that time does not have a fixed reference frame, and it passes differently for each person relative to another. You might be a bit surprised and confused by what I'm about to say, but imagine you live in a 5-story building. You live on the first floor of this building, and your friend lives on the 5th floor. Because you, who live on the first floor, are closer to the curvature of space-time compared to your friend, time will pass slower for you relative to your friend, and you will remain younger than them. However, at such very small scales, since this time difference is extremely negligible, it can be disregarded. Therefore, this is why Newtonian physics works flawlessly to such an extent. But if this distance becomes as large as the distance from the surface of the Earth to the GPS satellites responsible for transmitting GPS data, this time difference also becomes larger, and Newtonian physics no longer provides accurate answers. Instead, we need to use Einstein's general theory of relativity equations. Because this time difference between you and the satellite becomes so significant that you can no longer accurately determine your precise location, and you will be confused. So far, we have become acquainted with one of the applications of Einstein's general theory of relativity and demonstrated that this equation works accurately. Most importantly, we have also explained gravity from Einstein's perspective. But a big question arises. If all celestial bodies are exerting gravitational force on each other, and everything is attracting each other, then why is the universe still expanding at such a speed and not collapsing back into a single point like the Big Bang? If you would like, I can create a separate video to answer this question. Please comment "Create Part 2" in the comments section if you're interested. I hope you enjoyed watching this video. In the video on the right side, we explained how one can travel with gravity.